you have ever brought up interstellar travel in a conversation, people will quickly start saying things like, we need a warp drive for that, or we need a black hole antimatter fusion drive for that, or we need wormholes, ha ha ha. Well, guys, most of these ideas are actually nonsense science fiction, and we can actually do interstellar travel with the current technology that we know about today. Interstellar travel to hundreds of stars is highly likely within the next few thousand years, and all we need to do it is a little bit of patience. Okay, so if you didn't already know this, our sun is actually surrounded by a neighborhood of other stars. And in fact, within 12 light years of our own star, there's around 20 other stars. And the closest one of these is Alpha Centauri and Proxima Centauri, and they're about 4 light years away. And in the plane of the sun, they're only around 1 or 2 light years away, but they're actually around 3 light years to the south of us. And so here is where Alpha Centauri is in the local area. Now, there's a lot of argument about the habitability of other solar systems and other planets, especially our surrounding stars. But the biggest thing that people are not realizing is you don't need liquid water to actually go and settle a solar system, okay? As long as you can have robots and advanced humans go there and start exponentially increasing the amount of solar that they can generate, then you basically have unlimited potential for civilizing a solar system. Now, you also need to consider the relative motion of all these different stars. Okay, so for Alpha Centauri and Proxima Centauri, they're actually moving towards us at 20 kilometers per second radially, and then they're also moving perpendicular to us at 20 kilometers per second as well. So this was actually surprising me for a couple of reasons. I didn't realize that they were moving towards us, and I also, just looking at these speeds of around 20 kilometers per second, this is actually way, way slower than I expected. Okay, and the last thing it says here is that in around 30,000 years, Alpha Centauri and Proxima Centauri will pass within 3 light years of Earth and of the Sun. So, when we need to consider how much we need to slow down once we get to these solar systems, it's basically going to be the square root of 20 kilometers. That should be squared in there on those two, but it ends up to being around 28 kilometers per second, plus however much delta V you use to transfer there. Okay? And now if we do the math for how long this could take, using pretty reasonable speeds, as you can see here, you're looking at around 30,000 years, 20,000 years, and 10,000 years, for basically different levels of difficulty. And when you use the lowest level of difficulty at around 30 kilometers per second, this is actually incredibly easy, and we could do it with pretty basic technology that we know about today, assuming we can expand into the asteroid belt and things like this. So this is based on the rocket equation as far as when you're determining how fast you can make your space probe go. And so this equation is really simple. It just means delta V, which is how much acceleration you get, and then the velocity of your exhaust, and then the natural log of the fraction of how much fuel you use. Okay, so when you use something like hydrogen for fuel, when you're burning hydrogen, it's around 460 seconds of specific impulse. So what this means is if 90% of your spacecraft is hydrogen fuel, then you're going to be able to increase your speed by 10,000 meters per second. Now, we also have these electric thrusters that we also have today. And in fact, Starlink uses this to keep their satellites in orbit around the Earth. But the only issue here is when you're trying to do an escape velocity from a planet, you need a lot of impulse very fast. And so you're going to need to use a chemical rocket, pretty much. Or a nuclear chemical rocket, something like this. The continuous low thrust from electric thrusters isn't going to do it. However, you can use these thrusters to make that trip to the other solar system much shorter, okay? So when you do a 75% mass fraction with something like argon, which is current Hall effect thrusters, you'll get around 34,000 meters per second. And if you kind of use the future, and this is also today, with xenon, you get around 56,000 meters per second. So you can see that's plenty as far as increasing your speed when you're going to another star. And actually in the future, we can get up to 8,000 or 9,000 ISP. And this basically means if you're having something like a 75% mass fraction, you can increase your speed by up to 120,000. So if you have 2 of these stages, you could basically do that fastest possible route, and you could get there in around 10,000 years, or shorter, as we'll see. Okay. Now, the important thing here is the thrust-to-weight ratio, because we're going to be using something called gravity assist and an Oberth burn, okay? And the electric thrusters are not fast enough to make this work. By the time you go in and out of Jupiter's gravity field, the electric thrusters are not going to be able to produce enough thrust, okay? So you need chemical thrust. Now, the way that a gravity assist and an Oberth effect works is that we're going to be using the gravitational field of Jupiter to give us extra delta V, okay? And so this works in a few ways. But you can see here, as you get closer and closer to the center of Jupiter's gravity field, it's going to accelerate you up to 50,000 meters per second as you get closer and closer to the top of the clouds. Okay, now the way that a gravity assist usually works is that we're using the angular momentum of the planet around the sun, and we're sort of stealing some of that momentum in the frame of the sun, okay? So in the frame of Jupiter, the speed that you have going in and the speed that you have going out is the same. But from the perspective of the sun, some of this momentum is actually getting transferred, and your velocity relative to the sun is going to increase. Okay, so if the star you want to go to is in the same plane as the sun, you can actually do multiple gravity assists. And so this is what Voyager 1, Voyager 2, and the New Horizons spacecraft from NASA, which are pretty much the only spacecraft that have actually left our solar system, have done. They used all their delta V pretty much from gravity assists. Now, it's important to note that this is only going to work for stars that are in the same plane as the ecliptic, or in the same plane as the sun's rotation. But if they are in this rotation, you could get a lot of extra delta V, okay? For example, here's Voyager 1. It got 10 kilometers per second and 5 kilometers per second from Jupiter and Saturn. And this is without doing an Oberth burn, which is what we're going to be talking about next. So these are the other stars that are basically within the same plane as the sun. And you could actually make an argument that these are easier to get to because of these easier gravity assists. So you can actually use that relative velocity from Jupiter or some other star, and then you can also use several planets as gravity assists. So it's going to be a lot easier, but all these stars are further away from Alpha Centauri, so it's not exactly always going to be easier. Okay, now since Alpha Centauri is south of us, or you could think of it as below us if you live in America, we're going to need to go out of the plane of the sun. And this is basically impossible to do from Earth unless you use a gravity assist, like something like Jupiter. And this is because we're already going 40,000 meters per second this way around the sun. And so if we wanted to burn enough to go 40,000 meters per second this way, it's basically impossible. Okay, so what we're going to do is we're going to fly over the north pole of Jupiter, and it's going to shoot us down below at the perfect angle, and you can kind of work out all these different trajectories. And we're going to be going towards where that star is going to be in, say, 10,000 or 20,000 years. Okay, we're aiming to where the puck is going. Okay, now this isn't some sci-fi concept. This has actually been proven to work. And this is the Ulysses spacecraft from NASA. So the point of this spacecraft is they wanted to look at the poles of the sun, both the north and the south pole. So they basically did a gravity assist from Jupiter and flew right over the top of it, and then got really close to Jupiter's gravity field, and it basically launched it down to the south from the sun's reference frame. And so this seems like really counterintuitive or breaking some laws of physics, but you can go on the NASA Gravity Assist website, and they basically sort of explain that it's one of these weird physics scenarios where you have these different reference frames, and in certain reference frames, it seems like the momentum is not conserved, but you're actually conserving energy and momentum overall, of course, following the laws of physics. But yeah, it's very unintuitive. I'm not really even able to wrap my mind around it myself. So, okay, now the second thing that we're going to be taking advantage of is called the Oberth Effect. So the way that Oberth describes this mathematically is that the lower you are in a gravity field, the faster you're going to be going. So if you increase your velocity at a faster speed, that's going to increase your kinetic energy by more. So when you eventually have your escape trajectory, you're going to give back less of that kinetic energy to the planet or star, and you're going to have a higher escape trajectory, okay? So, and this is a sort of weird advanced astrodynamics thing where you can actually decrease your speed to get closer to the star and then increase it again, and you'll actually have a higher escape trajectory if you just burned from your initial position. Okay, so we're not going to be doing this with the sun, but we probably want to be doing this at Jupiter. Okay, and so I'm not going to explain this in the same way that Oberth described it, but basically what's going to happen is that as we get deeper into Jupiter's gravity field, it's going to be accelerating us more and more. Okay, and once we get to the deepest point, which is called our periapsis, we're going to be going at our maximum speed. Okay, now at this point, we're going to start a burn and we're going to increase our own speed. And what this is going to do is this is going to decrease the gravity loss of our spaceship. And the way that the laws of physics are still accounted for is that the exhaust that we shoot behind us, we're going to shoot that momentum deeper into Jupiter's gravity field. So it would have escaped before, but now it's going into Jupiter. And for that same reason, we're going to have less effect by that gravity field, but we get to keep all of that acceleration that we got by going into Jupiter's gravity field. Okay, and by the way, this is going to be heading down south. Okay, so we're flying over the top of Jupiter. Once we become perpendicular to the gravity field of Jupiter, that's when we're doing a massive burn, maybe like 5,000 or 10,000 meters per second. And that's going to shoot us back out to the south under the sun, and it's going to point us to wherever we need to go. Now, depending on how fast you're going, and it's actually the faster you're going, the more extra delta V you're going to get from this. So if you're going 50 kilometers per second, which might be a little bit faster than this basically easiest plan, you could get 4.58 times the delta V that you put in, because you're going to be stealing it from the gravity field of Jupiter. And in some ways you're not, because the exhaust that you put out is going to be going back into the gravity field. Okay? So, and again, this sort of has a limit, which is that the gravity field of Jupiter is only so strong, and you can only get up to 50 kilometers per second of acceleration, because if you try to get more than that, you're going to need to be going within the radius of the planet, so that's impossible. The only situation where you could do something like that is like a black hole, where it has like almost no radius, but it has tons of gravity, okay? But I don't know of any black holes that are nearby, so unless you guys do, you can let me know in the comments. Okay, now back to our rocket equation here. So we're probably going to go with hydrogen for this burn, again, because we need to have an impulsive burn. It needs to be fast. We're not going to be in the gravity field of Jupiter forever, especially in that really fast region. Okay, so we want to do 5 to 10,000 meters per second of delta V with hydrogen. And so you're looking at about 75% of 90% of your total mass of your spacecraft that you're going to need to burn within that, call it 30-minute or so period. I'm not sure exactly how it would last, but. Okay, now we get to the concept of escape velocity. So escape velocity is actually a technical term where you have enough speed to get out of the gravitational field of whatever it is, the planet or solar system. And then as time approaches infinity, your velocity gets closer and closer to zero, okay? And so this is higher from Earth. You need around 20 kilometers per second, but out of the asteroid belt, it's only going to be around 7 kilometers per second. Okay, now there's this concept of gravity loss. So it's very similar to the Oberth effect in how it works, but basically, when you're escaping from a gravity field, the slower you're going, the more of your velocity that you have at the periapsis you're going to lose. Okay? So if you increase your velocity faster than the escape velocity, then you're going to be able to save more of that periapsis velocity, and you're going to be able to keep it as relative velocity when you're traveling to other stars. Okay? So if you want to have a ton of escape velocity, it's actually kind of a smart decision to go closer into the field somewhere like Earth. But overall, it's actually way easier to do it from the gravity belt, because you don't actually need to be going 100 kilometers per second when you leave. You only need to be going 30 kilometers per second, like we said before. So here you have around excess velocity of 13 kilometers per second. So when you add it up, you actually only need 20 kilometers per second of delta V total to escape the Earth and go to our other solar system in 30,000 years. Now, going back to our Oberth burn example and the gravity assist that we're doing from Jupiter, we only need around 5 kilometers per second of actual delta V from the hydrogen rocket to get this 20 kilometers per second towards the star we want to go to and where it's going to be. Okay, and one more thing that's going to be helpful for us is that slowing down is much easier than speeding up when it comes to interstellar travel. So first of all, everything that is orbiting the Earth is going around 10 kilometers per second. And when it re-enters, it could just use the atmosphere. And you can see something like Starship, probably 99% of the velocity is just slowed down by the atmosphere. Okay, so that's 10 kilometers per second right there. The second thing is you'll also have sunlight again. So you can end up using solar panels for your electric thrusters instead of using nuclear power. Okay, so when it comes to the easiest way that we could possibly do interstellar travel, this is basically what it's going to look like. Okay, so we're going to leave from the asteroid belt. And again, we're going to create all of our fuel, all of our chemical fuel from asteroids like we talked about in our last video. And we basically need 5 to 10 kilometers per second to point us to Jupiter, to fly over the top of Jupiter and not get sucked all the way in. And then we're also going to need 5 to 10 kilometers per second to do the burn at the periapsis at Jupiter. Okay? And so this is basically all that we need for escape velocity. But then in interstellar space, we can actually use as much as we want with our electric thrusters, as long as we speed ourselves up and then slow ourselves down in equal amount. And actually, we'll need to slow ourselves down a little bit more because of that relative velocity that I talked about earlier. But again, that's at the very end of the interstellar trip. Okay, so what this looks like when we talked about the rocket equation before, it's going to work around 1 to 2 hydrogen stages, where 90% of that is fuel. And then also you could add 0 to 2 electric stages, and around 75% of that mass is going to be fuel. So it's just a trade-off of how fast you want to go and how much mass you want to bring. So at minimum, I'm thinking it's around a 95% mass fraction that's going to need to be fuel and propellant that you exhaust from your vehicle. Okay, and that's actually way less than I expected. However, if you want to go there very fast, in something like 10,000 years, you're going to need to use many more stages, and it's going to be exponentially less mass that you get. And so you can see the number there, it's very small, but actually still sort of doable. So when it comes to the staging, the larger that your rocket is and the larger that your spacecraft is, the lighter that your fuel tanks are going to be, which actually really helps out for this interstellar travel scenario. So you can see the sphere here. Basically, the surface area increases with the square, and the volume increases with the cube. Okay, so this means that you're going to have most of your stage or most of your rocket is just going to be your payload, where the people or robots live or whatever, and then your fuel. And not very much is going to be dedicated to the fuel tanks. And of course, you will need a lot of mass for the engines. But again, on rockets like the RL-10 on Earth and for upper stages of rockets, it's usually much, much less than 5% of the rocket is the actual engines. Okay, another point is that this does have a limit. Okay, we can't just have planet scale spacecraft. And well, we can kind of, but the point is when you're getting really close into the gravity field of Jupiter, you're going to have super strong tidal forces. And so this means that your tanks are going to be experiencing a lot of force, and you're going to need to make them very thick and heavy if you want to survive those tidal forces. And so the size of your spacecraft is ultimately going to have some sort of limit. Okay, like we talked about before, why not go way faster? Okay, and this was the trade-off between how much mass you're going to be bringing there and how fast it's going to be. So you can see if you start out with a 1 million ton ship, by the time you burn all your chemical stages, you're looking at around 25,000 tons that's actually going to be usable. Okay, and then if you do a bunch of different electric stages, then you might end up with only 100 tons if you want to get there in something like 5,000 years. Okay, now this is actually a viable option because, like we talked about in the last video, you don't actually need that much mass to settle a solar system. And this is because of the robo-habitable zone. All you need is enough mass to create an exponentially increasing solar farm. Okay, so if you had a robot and solar system, a silicon refinery, if in 1,000 years from now, if we could fit that into 100 tons, then we could start a robot colony that gets there 5 to 10 to 20,000 years before humans, and it can set up the whole solar system before we even get there. Okay, and now I sort of imagine it looking like this. You basically have a 100-ton spacecraft that lands, and then you have this AGI robot that comes out and all these other refineries and stuff, and they could basically just start exponentially expanding through the entire solar system and take it over. Now, this is sort of a bad idea in some ways because, if we have AGI robots, they're going to be incredibly smart. They're going to have a mind of their own. And so giving them the power over the entire solar system, basically making them God King of an entire solar system, uh, might not be the best idea when we show up 15,000 years later. I mean, imagine how much humans have advanced in 15,000 years. Um, this robot colony is going to be doing their own science and their own advancement, and they might decide that they want to go explore the rest of the galaxy before humans even get there. So this is risky, but I think it's a good idea if we trust our robots. Okay, now as far as the whole mega spaceship idea with tons of humans that just live there for 10,000 years, it's actually super doable. And obviously, it's easier to do a small one. Okay, so you could have something like the Wall-E spaceship where we're all fat and drink smoothies, or you can have something like the Death Star. Okay, but you could also have a much smaller spaceship that would get there much faster, and this would actually be cool. But you need them to use a lot less resources. Okay, you need them to use a lot less power, in particular. Okay, and so I sort of imagine this like if you've seen the Fallout show, they have this vault where it's like 3 vaults, and they like live pretty poorly, and they trade people every like generation. They'll trade a few people to like keep the genetic diversity, and maybe they'll have like frozen sperm and eggs or something, just so everyone doesn't end up inbred. But yeah, I sort of imagine something like this, and it's kind of creepy and dystopian, but I think it's actually equally creepy as the Wall-E ship. So I don't know. Okay, now to make one of these ships, oh yeah, first of all, let's assume it's like 1 million tons, like a Wall-E ship. So Elon Musk says you need 1 million tons to have a self-sustaining colony on Mars. Well, that's probably basically true as well for a spaceship. And maybe not in 1,000 years, it's probably less. But for something I'm imagining today, it's probably 1 million tons, okay? And so 95% mass fraction, you're talking 20 million tons or 100 million tons of fuel. Okay, and then for a Fallout size ship, you only need 200,000 tons or 1 million tons of fuel, which is actually like incredibly low amounts of fuel. But again, you're gonna have to harvest this from an asteroid. Okay, it's not like you could just bring it from Earth, because again, you have to use 10,000 meters per second to bring the fuel from the Earth into Leo, and then you have to have an even more higher escape velocity at Earth. Okay. Oh, and by the way, a lot of this mass, actually no, not that much mass, but a little bit of the mass is going to be uranium or fusion fuel in a reactor. Okay, so it's not all going to be able to get used by humans. Okay, now as far as how much fuel you need, the size of the ship is also going to benefit us with the square cube law, because again, there's no real temperature in space because there's no particles. So the only thing you have to worry about is the radiation coming from the surface of your object, and the bigger your object is, the less surface area, the less relative surface area it's going to have, and so it's not actually going to be a very bad thermal situation. It's going to be pretty efficient. Um, and so, I mean, this is just kind of a rough guess, but you can adjust it and it still kind of makes sense. But if you wanted 500 kilowatts for this space station, you'd probably want more, which is fair. But if you want 500 kilowatts, you only need 2 tons of pure uranium 235 over 10,000 years. Um, and so that's actually a pretty good option. And you need a lot of mass for the reactor, but whatever. Now, plutonium could also be useful, except its half-life is 24,000 years, so it's going to be decaying. So if the power source was based on the decaying of plutonium, maybe it would work, but that would cause some issues. Okay, and then fusion. I haven't really looked into fusion. I'll probably make a video about fission versus fusion in the future. I was talking about that with someone I know. But I'm just kind of having that as a question mark. I don't really know what to think about it right now. Okay, now, as far as getting 100 million tons of H2O, this seems like totally impossible today, right? For making the hydrogen and oxygen fuel. But it's actually like incredibly, incredibly doable. And honestly, like if you watch my last video where I said this would be done in like 200 or 300 years, I I think that this type of ship is also possible in that time frame. Okay, and you'll see why here. So 100 million tons of H2O, you're basically going to need to use electrolysis on water, and this is going to need a lot of energy, but it actually only works out to like 4.2 gigawatts of energy. Okay, which is like, there's probably some steel mills in China where they use this much power. Okay, it's really not that much. And like we talked about in the last video, um, the amount of power that we could generate in the asteroid belt through these exponentially increasing solar farms is like in the terawatts just for one asteroid, for the largest asteroid of series. So yeah, this is super doable. at least within 1,000 years, if not within hundreds of years. Okay, now how many Wally like we have a limited amount of water, so that was something I was worried about. I was like, oh no, are we going to run out of water when we make these spaceships? Well, if we made these spaceships like 10 stages and they had like a 0.001001% mass fraction, then we would run out of resources. But if you only have a reasonable 99% or 95% mass fraction, then you only need 100 million tons of water. Okay, and when you compare that to amount of water on Ceres, you could do 2.35 billion of these missions out of the asteroid belt. And then if we run out of the asteroid belt, which I can't imagine, but let's just say we run out of materials in the asteroid belt, then we still have 14 billion Wally missions worth of water in the oceans on Earth. Okay, and then worst case, even beyond that, we could start doing like fusion experiments. Not really experiments, but you could do fusion to create elements and stuff. I might make a video on this later as well. But if you had future tech, like you basically have endless amounts of these galaxy exploring and solar system exploring missions, and then each one is going to be able to spread out many more. Yeah, guys. So I basically see this as super easy, and it's basically just being an exponential expansion into the galaxy and just taking over more and more and more stars every 10,000, 50,000 years. Now, if it goes wrong, say we send robots to one of the solar systems and they take it over and they try to nuke everything that comes into the solar system, they basically are going to have an advantage. I'm actually probably going to make a real Star Wars video at some point, but they are basically going to have an advantage as defense because they don't have to do all that staging to get the nukes to defend themselves, whereas we need to send nukes with a bunch of stages and stuff. So that would be challenging. Of course, you could try to do like stealth nukes and stuff, but anyway, if that goes wrong, we still have an infinite number of stars in the sky, and so we could just be a little bit more patient and make our trips last like 100,000 years or a million years. A million might be pushing it, but yeah, we could just go to different stars. And even in our little group, in our 12 light years around us, we have 20 different stars. Okay, now, if you've ever played the game Starfield, which I know people hate that game, but there's this point where you're coming from Earth with an advanced spaceship, and you meet these settlers who left like thousands of years before. And so it's pretty funny in this situation, but as our technology gets better and better over time, we're going to be able to pass these earlier generations of settlers and starships. So if we expect to get there in 30,000 years, probably humanity is going to be so advanced 30,000 years from now that they can probably get there in like 1,000 years, and they're just going to get past us. So it is kind of pointless in that respect to go so slow. We should do it anyway. Just as a sort of optimistic thing to do. Okay, and then as far as why people are going to be doing this, people are going to be dying to do this, okay? And the reason is, if you see all these sci-fi movies and stuff, they always have like a founder or leader or something, and maybe we'll have like cyborgs in the future that can live forever and stuff like this. But basically, if you get to a solar system and you have control of all the resources, okay, as the landowner of that solar system, you're like incredibly powerful, like unbelievably powerful by today's standards. And then, of course, you're going to be able to keep expanding into the universe for whatever star you go to. So people are going to love to explore. And throughout human history, obviously, people obviously like to expand and explore, always. Okay, yeah, so yeah, I think this is a really beautiful idea, actually. And it sort of makes me think, like, it's really interesting that this isn't in the zeitgeist, and there's sort of this narrative out there that we need all this, superhuman advanced future technology to go visit other stars. But in reality, it's totally normal. And it's almost like the universe has this sort of balance and design where it's we reach this stage of technology and we're able to visit all these other stars easily. And so, yeah, it reminds me of the sort of the stages if you've ever played the game Spore. We're just reaching out further in the tech and future in technology, and we're going to be able to explore the whole galaxy. I don't really see any laws of physics that are preventing it. So that's sort of going to be some of the future videos in the series. We're going to be talking about all the things I mentioned and then exploring the galaxy. I'm actually not sure if we can go to other galaxies, so that's going to be a fun video as well. Okay, guys, hope you like this one. I thought this was a lot of fun to make, and so I'm really looking forward to the rest of the series. But if you got this far, make sure to subscribe, like, and leave a comment about what you think. And of course, thank you for watching, and have a great day.